There's something rather magical about radio waves. They're actually a sort of invisible energy. This aerial can actually pick up enough of this energy to power this primitive receiver I made. It has no battery. It relies entirely on harnessing the energy of the radio waves in the air. It's not very loud, so I'll have to put it straight on the microphone so you can hear it. I managed to pick up Radio Israel broadcasting from Jerusalem on it one night. Although there's something quite wonderful about this little thing, radio sets have been around for so long now that they've become rather ordinary, unglamorous contraptions. And even the electronics inside now look rather familiar. In this programme, I'm going to look at how these mysterious radio waves were discovered and how radio receivers managed to pick them up. Creating radio waves is actually very simple. Any electric spark emits them. Each of these sparks is sending out radio waves. You hear them on the radio as interference. That's why lightning makes radios crackle, and even the tiny spark inside a light switch is enough to produce a little pop. But without a radio set, though, it's not easy to detect these waves, and most scientists didn't believe they existed till just over 100 years ago. What finally convinced them was an experiment performed by the physicist Heinrich Hertz in 1887. It was first demonstrated in Britain by a scientist called Oliver Lodge, here in the Royal Institution. Hertz used very big sparks created by a machine like this called an induction coil. Could you turn it on, Bill? This was connected to these metal plates with another spark gap in the middle, and this acted as a sort of aerial. This was Hertz's receiver. It's simply a loop of copper wire. Well, the big spark creates radio waves with enough energy to make a tiny spark jump across the gap between these balls in the receiver when they're held very close together. So, I hold these in position. OK, Bill. If you look carefully, you can just see the spark jumping across the gap. These sparks are so tiny that Hertz had to let his eyes get accustomed to the dark for 15 minutes and then watch the sparks through a magnifying glass. His apparatus only had a range of a few meters, and he had no interest in finding any practical uses for it. The first person to use radio waves for signalling was Guglielmo Marconi. Marconi had been a difficult child. His mother was a Jameson from the Irish whiskey distillers who'd run away to Italy to be an opera singer and married an Italian landowner. She quickly got bored on his estate.
There's not much going on here. I think we'll go for a little jaunt.
The infant Marconi spent much of his childhood being dragged round Europe by his mother.
Where are we going, Mama?
Barcelona, or perhaps Boulogne.
Gatti colorati, la 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 la, eccolo, eccolo lì, la 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 la.
He showed little interest at school and constantly irritated his father with ridiculous scientific experiments.
Qua sei? Eccoci. Eccola. E vamos!
Mi prego uma plate, a smash your face.
Shortly after failing to get into university, he happened to read an article about Hertz's work.
Oh! Hey.
He immediately started obsessively experimenting and had soon managed to transmit the signals over a mile. Still aged only 20, he arrived in England to try and sell his ideas. Marconi had found that fixing one side of the spark gap to a long vertical wire made a much better aerial than Hertz's. This was further improved by connecting the other side of the spark gap to Earth. Apart from that, the transmitter was basically the same as Hertz's. Any electrical spark will do. Here it's being provided by the ignition circuit of Rex's pickup truck. This primitive transmitter has a surprisingly long range. Marconi also used a much more sensitive receiver called a coherer. This was based on a design by Oliver Lodge. This is my homemade version. It's just a tube of nickel filings. I made it by filing down a coin. You fix one end to the aerial, another kite, and the other end to the earth. And what happens is that when it detects the radio waves, its electrical resistance falls dramatically, so it acts as a sort of switch and turns on a circuit. The theory behind it's very complicated and wasn't worked out till many years later, but it's quite simple to make it work. The only slightly complicated thing is that you have to have something to shake it to restore its high resistance at the end of each signal. So now if I signal to Rex, this is Marconi's original equipment that he brought to England with him. This is his transmitter with an induction coil like Hertz's and these balls that concentrated the energy of the spark. One end would have been connected to the aerial. This is his receiver. The aerial went on here. This is his coherer inside the glass tube. The filings are actually in the gap in the middle. And this is the device to tap it. Marconi would have been sending a combination of long pulses and short pulses, sending messages in Morse code. Well, this original apparatus only had a range of about 3 miles, but Marconi gradually increased the sensitivity of his coherers and the size of his transmitters till he was sending messages hundreds of miles. The larger transmitters had much larger spark gaps, which got very noisy, so he had to take to putting them in enclosed boxes. Marconi's early systems had a big disadvantage. They couldn't be tuned. You can hear the signal from our spark transmitter all across the short, medium and long wave bands. The reason is that sparks create chaotic waves of all sorts of different wavelengths. What was needed was a more precise transmitter than a spark. This was the solution, the tuned circuit. It suddenly all starts to look like a proper radio, but the basic parts are still quite simple. There's a coil of wire here called an inductor and a series of overlapping metal plates here called a capacitor. The electricity whizzes backwards and forwards from one to the other, oscillating thousands of times a second. The valve acts as a sort of pump, keeping the whole thing going. You can see a picture of the radio waves this tuned circuit's transmitting on this oscilloscope that I've hooked up to a short aerial. If I hold it near the tuned circuit and switch on, you can see how regular the oscillations or waves that it's transmitting are. Now, if I compare this with the spark machine, you can see just how chaotic its radio waves are. Once the tuned transmitter had been perfected, spark transmitters were quickly banned for polluting the airwaves. With the problem of interference solved, radio seemed so miraculous that it could be capable of almost anything. Early radios did still have one limitation. They couldn't transmit speech, only the simple pulses of Morse code. Morse code's still used for messages on the shortwave band, and pulse codes are also used for radio-controlled models.
built this little car for a children's television series, and I've hooked up the oscilloscope to the transmitter so you can actually see the stream of pulses that the car receives. If I work this switch, that's the one that works the headlights, you can see it just moves one pulse. If I shift that one, it works two pulses, which actually opens the door. This one works the steering from left to right, you see it's moving four pulses. This one is shifting 5 pulses, and that's the speed control for forwards and backwards control, and so forth. Each series of pulses work a different function inside the car.
To transmit speech and music instead of simple pulses, you first have to convert the sound to an electrical signal with a microphone and then combine it with the radio waves. In the radio receiver, it all gets separated out again. You can see this very clearly on an oscilloscope. If I turn on this little radio, and I now plug the oscilloscope in to the loudspeaker, it's a bit large, this is giving a picture of the sound signal, and you can see it roughly matches the sound that's coming out of the loudspeaker. Now if I plug it in further back on the circuit, this is the sound signal combined with the radio waves. You can see the peaks still roughly match the sound that it's making, and the radio waves are actually going rapidly up and down in the middle. Now if I stretch this out a bit, these are the actual radio waves, and you can see what's happening is that the sound is constantly changing their size or their amplitude. And that's why this is called amplitude modulation, or AM radio. The man who designed much of the practical circuitry for AM radio was an American called Edwin Howard Armstrong. While in France during World War I, he invented the superhet circuit, which has been used ever since. He then sold a patent to RCA back in America.
I have an appointment to see Mr. Sarnoff.
Oh, Mrs. Sarnoff's expecting you, Mr. Armstrong.
Thanks.
You're welcome.
He became a millionaire overnight and fell in love with the chairman's secretary.
How about you come for a spin in my motor?
Okay.
Hop in there.
Oh, it sure is a big one.
He bought a huge Hispano Suiza and climbed his tallest aerial to impress her. They were married soon afterwards.
Will you marry me?
Oh, Howard, my hero.
The fundamental principles of radio have remained unchanged. This is the BBC transmitter at Brookman's Park, broadcasting medium-wave radio to southeast England. Inside, the engineers have restored the BBC's very first transmitter, built by the Marconi company in about 1920. This end of it actually creates the radio waves, and this end of it combines them with the sound signal, the amplitude modulation. It's basically a series of giant tuned circuits with the valves, the coils of wire of the inductors, and the overlapping metal plates of the capacitors. Well, this generates about 2 kilowatts. This may sound a lot, but this modern transmitter is rated 150 kilowatts, and it's all much more sophisticated. This one's actually broadcasting Radio 3 on AM all over southeast England. Inside, though, the basic components are still remarkably similar. The inductors have remained exactly the same, and the valves and capacitors, although they're now more enclosed, still work on the same principles as well. Transmitters like these, broadcasting sound, first appeared in World War I. They were used for sending messages by radio telephony. Broadcasting radio to entertain people was first started after the war by enthusiastic Marconi engineers. The BBC was then set up by the government in 1922, and listening to the radio rapidly became very popular. At first, most listeners had very simple receivers, crystal sets like the Rexophone. They needed enormous aerials because, like my radio at the start of the programme, they had no battery and relied entirely on the energy of the radio waves in the air.
Looked back on the literature they'd been taught in these academic institutions, they found it wasn't really their literature.
It's easier to see how they worked on this homemade version. Instead of a coherer, it has a lump of crystal and a fine wire called the cat's whisker. Electricity will only flow one way through the contact between the wire and the crystal, and this has the effect of separating out the sound from the radio waves. Like the coherer, the theory behind the cat's whisker is very complicated, but it's quite simple to make it work. The imperfect contact between teeth and fillings can occasionally have the same effect, causing a few unfortunate people to hear the radio inside their head all the time. This is the modern equivalent of the cat's whisker, the germanium diode. If I put it under a magnifying glass, you can see it's an enclosed version of the same thing. You can see the whisker just touching the lump of germanium. The primitive radio I had at the beginning of the programme worked with one of these, and in fact most modern transistor radios still use them as well. Much of the radio set's evolution has been preserved by Gerald Wells at the Vintage Wireless Museum. If you wanted something better than a crystal set, what sort of thing would you have had?
Well, you could have had something like this, which is 3 separate units, hence it was called a wireless or radio set, because it was a set of parts. It would have consisted of a tune circuit, an RF amplifier, a detector stage, and a power output stage. And that would have got you most of the local stations with earphones or a modest loudspeaker.
What happened after that was the next stage?
Well, the next stage, they decided to stick it all in one box to make it less wires and to make it neater. This was a bit more elaborate as well. More stations were coming onto the airwaves, so more elaborate tuning was needed. So they brought in series parallel switching for your aerials and tune circuits, variable condenser and reaction condenser, an RF stage to amplify the signal, a detector stage to take the place of the old-fashioned cat's whisker, and 2 stages of LF amplification. That would be quite an elaborate set, but you could, by moving these bars around, do away with those stages and listen with earphones on there and save a lot of battery power.
Oh, I see. When did they start enclosing all the working parts of the radios?
Well, certainly by the mid-20s, when they decided that this wasn't really very nice in the living room, and so they started building it into familiar objects, like the medicine chest, for instance, where it could be easily disguised, and that wouldn't disgrace any respectable home.
What other shapes?
Well, the most famous of all, of course, is the smoker's cabinet. Every home had a smoker's cabinet. You'd have your pipe racks and your bits at the top. Smoking was big industry. You'd have your drawer at the bottom, where you'd have your pipe cleaners and your matches and your tobacco, and it would all fold away and look quite innocent. It didn't scream wireless at you.
Of course, all these early radios were powered by batteries, weren't they?
Well, yes, there was very little electricity around, and the early radios required a 2-volt accumulator, sometimes 4 or 6, but usually 2, which had to be charged up every week, so that meant you had 2 of them, 1 being charged, 1 in use, and you'd need a high-tension battery, you'd need a grid bias battery. The grid bias battery lasted about a year and cost 9p. That would last about 3 months and cost you 7 and 6p.
So it was all quite expensive then?
It was an expensive business, and it took a lot of rigging up. You had to have an elaborate aerial and earth system, and all the bother of getting your accumulator charged every week. Admitted it was only frothless and reasonably cheap, but it did mean you had to be careful. You had about 20 hours listening a week. So that when you went to your radio shop, there was usually a Radio Times provided on the counter. That saved you buying one. And with the aid of their Bakelite fountain pen and a pad, you could make notes of what was worth listening to during the following week. So you could pick your programmes and plan your meals around the wireless set. You didn't just hear it, you actually sat down and listened to it and gave it all your attention. You had to, it cost you so much to rig up. And of course, when you came in with your accumulator every week, there was all the other old tabbers and rat bags in there changing the accumulators as well, and you would discuss the programmes. So the reputation of wireless programmes was made and lost in a wireless shop.
By the 30s, the appearance of radios had started to change dramatically with the introduction of the new material Bakelite. Pioneered in Britain by the Echo Company, this could be moulded to almost any shape. Its one drawback was that it was easily breakable.
See these two portable radios? Well, watch this. Let her go, Betsy. Sorry, friend, you old-style portables have to go. But look at our new RCA Victor portable radio. Came through without a chip. RCA Victor's non-breakable impact case means no chipping, no cracking, no breaking. And hear that tone. It's RCA Victor's great golden throat sound. See the world's only portables with the non-breakable impact case as low as $27.95 at your RCA Victor dealer.
The biggest change in broadcast radio since the war has been the introduction of FM. The great advantage is that it's much less susceptible to interference. The spark, which drowns out AM radio, is hardly audible on FM.
Mrs. Thatcher, why should use the phrase guerrilla warfare? Because there are...
FM stands for frequency modulation. The principle behind it is really quite simple. Instead of the sound altering the amplitude of the radio waves, as in AM, it alters their frequency. FM radio was yet another invention of Howard Armstrong. He started work in the early 30s with a missionary zeal to produce true hi-fi radio. After encouraging tests with RCA, the company suddenly pulled out.
Sarnoff! Well, why have you cancelled my project?
Get off my back. We
Hi-fi
never promised
radio
you
is
nothing.
the
We're
thing
into
of the
TV
future.
now.
When FM radio was becoming established, Armstrong and RCA started a lengthy battle over the patents.
You have stolen my ideas. You did not. I was the inventor. Certainly not. How can
This had a disastrous effect on his health and on his marriage.
Oh, I've had such a terrible day.
By the way, I'm leaving.
This is the last straw. I can't take any more.
FM has now become firmly established and is invaluable for radio communications as well as for broadcasting.
When I fly my little aircraft, I use radio. I personally wouldn't fly without one. This enables me to keep in touch with air traffic control and other air users, and also airfields, to tell them of your intentions. And if you do happen to get lost, air traffic control can help you find your way. And it also is a navigational radio. I can tune in to various fixed beacons throughout the country, and I can fly directly to and from these beacons. And that helps immensely to find your way around the country.
Domestic radios have also become much more sophisticated. Many now have automatic push-button tuning, and the sound quality can be very impressive, particularly in stereo FM. But despite this improvement, radio has really been eclipsed by television and other modern marvels, and radio sets aren't the important prized possessions they once were. In fact, the whole idea of a separate radio set is rather disappearing. Radios now tend to be combined with cassette tape recorders or alarm clocks or hi-fi systems. Radio is so taken for granted today, it's hard to think of it as magical anymore. But I hope in this programme I've managed to persuade you that it still is. I still find the idea of radio completely magical, that there's all this energy all around in the air. I'd never actually made a crystal radio before, but I would encourage anybody to have a go. There's something just very exciting about it. And I think at the time I wasn't so aware of the early history that to the Victorians the telegraph, the invention of the telegraph, so you could communicate at a distance, at first just by the dots and dashes of Morse code, and then with Bell's invention of the telephone, that you could actually send voices along the telegraph wires. And then with the invention of radio, that you could throw away the wires and just communicate through the air. No wonder they believed in telepathy and ghosts and all sorts of things, the ether. It gives me great sympathy for people like Oliver Lodge, who was rather discredited for his belief in the supernatural, but looking back it seems quite understandable, really. The coherer was amazing. I really wasn't expecting that that would work, just grinding up a coin. In some of the other experiments, which didn't reach the final film, we borrowed a coherer from the Marconi Museum. It was fortunate Marconi was still going as a proper company at the time and had a museum, and they were very helpful. But anyway, the actual bought coherer worked even better. I think that was ground some silver in it or something. It was smaller than the one we made. Oh, the other thing about the coherer was that it was fascinating sending wires up kites. The voltage difference between the ground and higher up in the air was enormous. Nothing to do with the thunderstorm, and I was left wondering whether there shouldn't be some clever way of creating energy out of this, these great voltage differences. We're all told not to send wires up kites because it's dangerous, but it was impressive. One lovely fact about the transition from spark radio to tuned radio, I didn't know at the time, was about the hackers in America. Because radio was being used for military purposes, particularly communicating to ships, the American government made it illegal for people to broadcast on spark radios because it interfered with their own signals. And this outraged some American amateurs, so much so that they sent out false messages to a destroyer moored off Boston and got it to change course. I love this idea of Victorian hacking. It has a long history. Another thing that I realised watching the programme again, or remembered, was just how rapid the rise in popularity of radio was, of listening to radio was, in the 1920s. People often talk about the accelerating pace of technological change, and I'm really not sure about that. Radio took off just as rapidly as mobile phones, I think, really. One final legacy of filming the radio programme was via Errol Davis, our consultant and curator at the Science Museum. He'd recently acquired a long-wave BBC transmitter from Yorkshire, and the museum declined to put it on inventory, so he was rather left with this thing. So anyway, I ended up with this absolutely magnificent gadget here, the final stage tuning capacitor from the transmitter, and it's been in pride of place in my office ever since. So how has radio technology moved on? Well, it's sort of become digital, but not completely. In the UK, the government made a fortune switching off the analogue TV channels and auctioning off the bandwidth to phone companies. So they then wanted to do the same with radio. They launched digital radios over 10 years ago, before they'd really got enough transmitters, called DAB radios. And they still haven't been able to switch off the analogue signals. I don't know, there's no particular date when that's going to happen now, so we still have both digital and analogue. More recently, of course, people are now listening to podcasts. So they're now listening to things that come through fibre optics and wires, no longer through the magic of just coming through the air. Bit sad, really.